So hello everyone, welcome all of you. My name is Shoaib Aziz and today we are going to study things about principle of navigation and specifically time standards. Okay, but before we begin into principle of navigation, we need to understand certain things such as what is guidance, what is control, what is surveying. Let me just put myself a bit down there. Let me see if I could, yeah, grab down over here, and I can open up my whiteboard, Microsoft Whiteboard. Great. This thing does not need to be here because we are not interested in knowing how to mug up the code of for finding the longest palindromic string. It takes a while to load, and okay, we're done here. So guidance. So if I start guidance, it's horrible. You need to understand it. Anyways, it's definition of a desired path and trajectory. This is guidance. Okay, then you have control. Uh, uh, Guidance is the definition of a desired path and trajectory, and control is how to get and maintain the desired path. And then we have surveying. And this is positioning of a non-moving object. Okay, positioning of a non-moving object. I think I should try to write less and explain more. Some of the questions that we get are: how do you navigate? How do you give directions? And how do you design a system to navigate? Okay, how to obtain PVT, which is position, velocity, and time, direction, relative to we do it relative to a baseline reference with a known position. Okay, that's how we find our position, velocity. We can measure angle, velocity, range, time, rotation, relative moment, dynamic moment, all of these things. To find our position, we can integrate a path or dead reckoning or instantaneous positioning. Okay, how do we design a navigation system? First of all, the most important thing in order to design navigation system is to build a frame of reference, to build a coordinate frame, to unify time and position, build reference, build I don't know, I think so this cable is not that good. I think probably I should try a different cable that's gonna work better. Sorry for that, guys. Let me see if this is any good or not. Build reference, no, this is build reference and coordinate frame. Okay, obviously if you are designing a navigation system, then you need a transmitter that is capable of transmitting reference position information. Okay, so we have a transmitter. Okay, for example, here is the transmitter, and this is, and for example here is something that we need to locate. Locate. So this transmitter is continuously sending its position to the object. Okay, designer receiver, easy to measure time of arrival, time delay of arrival, and Doppler, when we are designing any communication system, we need to take into account the Doppler also, because Doppler is, for example, you have got a sine wave. Let's say you have got a sine wave, okay, and you've got a person standing over here, and for example, if this is the object, let's say object, and if this object is moving with velocity v, so this sine wave is going to look a little bit more stretched or a little bit more squeezed, depending on if the person is moving away from the source or coming closer to the source. This one needs to verify. I'm not really sure about it, but I hope you give me benefit of the doubt here. Okay, let's pan the screen a little bit, and let's get back to drawing. And please, okay, let's use some different color. Time, standard, and coordinates we need to understand. First of all, the types of coordinates. Types of coordinates. So types of coordinates. Okay, so first we have Cartesian. Cartesian. Everyone knows that how to represent a Cartesian coordinate x, y, and z. Okay. Second we have polar, and as I don't know how to represent them, I'm going to do a quick Google search right now here, so that we can know, because these are all trial lessons for my own understanding and obviously your understanding as well. I would be really glad if they could mean something to you. Obviously they mean a lot to me. So let's do a quick chat GPT. Previously we used to say let's do a quick Google Google search, but now we say let's do a quick chat GPT. Polar coordinates. Polar coordinates are a way to describe a point in a plane using distance and angle instead of xy grid as usual. So we if we say polar coordinate, okay, let's start with Cartesian. This is the point. So it is going to have a x value, it's going to have a y value. I can write it x comma y. Okay. Now the same thing I can also do in a in polar coordinates. How do we do? We take a reference line, and for example, I want to locate this point. So my coordinates for this point are this distance r. Let's say this distance is r. Let's say this point is P, and we have a angle theta here. So my polar coordinates are r comma theta. Considering this is our reference axis. Okay, and of course if you want to convert between from polar to Cartesian, it's very simple. You take the x component. What's the x value of this r cos theta, and what's the y value is r sine theta, okay. And then we have geodetic coordinates. I think probably I should buy a new tab. Geodetic Okay, so let's do a quick uh, Google on how to find geodetic coordinates. So geodetic coordinates are used to describe a position on or near the earth using a curve ellipsoidal model instead of a flat plane. Okay, a point is written as phi, lambda and h, where phi is latitude, lambda is longitude, h is height. Okay, so makes sense. Okay, so for example, as we all know, let's say this is our earth and this is the equator, and we have some degree latitude over here, then some degree latitude over here, and some degree latitude over here. Okay, some degree latitude over here. It's negative latitude, by the way. Okay, and then we have also divided the earth by longitudinally. Okay, uh, so let's say like this, and now try to imagine it in 3D. Okay, if I want to locate any point on this grid, I can say whoops, here is the point. Okay, and if it has got a height, try to imagine it in 3D. It's h height above the point on the flat plane. So the way I represent this is phi, which is latitude, lambda, which is longitude, okay, and height. Okay, so we have geodetic coordinates, and when we are dealing with geodetic coordinates, it's very really important to to realize that we use an ellipsoidal model of Earth. Earth is not a perfect sphere. We use an ellipsoidal model of the Earth, which says, which is standardized as WGS84. This is a model of the Earth, and it is standardized, I think so, in 1984. Scientists from some astronomical community, sat up and decided, okay, we need to agree on one point, and that's how they decided this ellipsoidal model. This ellipsoidal model, 3D, probably I could show you in some in the following time, but let's continue on from now. I've already explained the types of coordinates, the major types of coordinates: Cartesian coordinates. And by the way, in Cartesian coordinates also there are some different reference systems. So let's go to that. Reference systems in Cartesian coordinates. And let's pan it. Got it. Reference systems in Cartesian coordinates. Okay, so first we have terrestrial reference system. So first we have a terrestrial reference system. Terrestrial reference system, which is earth-centered, earth-fixed. So earth centered, earth fixed. Okay, let me check if there are any settings which I think so my this is behaving pretty weirdly. Are there any settings that I could change? Yeah, there are some settings. Enhance ink shapes, format background. Okay, let's see how does this help. Let's select, oh actually I can also type here, yeah, it's better to type. And second we have inertial reference system, inertial reference system, sorry for that. And it's earth center initial, earth centered inertia. Now first of all we need to describe what is an inertial frame of reference. What is an inertial frame of reference? So we put in what is an inertial frame of reference. An inertial frame of reference is a coordinate system where objects behave in the simplest possible way. No force act on them. They either stay at rest or moves in a straight line at constant speed, which means they are non-accelerating. Okay. Intuition, for example, imagine you are in deep space far away from planets and gravity. You push a ball, it keeps moving forever in a straight line. Nothing mysterious, changes its motion. You pushed it, it's moving. Now, okay, a car is moving at constant speed on a straight road. Inside, objects behave normally, no extra forces felt. Non-inertial frames. Car is turning, something is happening, you are accelerating. Okay, that is a non-inertial frame. You must add fictitious forces. Uh, if any type of force or any type of pseudo force is acting on the frame of reference or on the object that is being studied in the frame of reference, then that is a non-inertial frame. Okay, is Earth an inertial frame? Well, not perfectly. Earth rotates and revolves, so technically it's non-inertial, but for everyday problems we approximate Earth as inertial, because yeah, that would inculcate us a lot of hardship. We assume that to be inertial frame of reference. For precise work like satellites and all, which we are going to study, we use frames like Earth-centered inertial frame (ECI), Earth-centered inertial frame, and Earth-centered Earth-fixed frame. So let's say what is Earth-centered Earth-fixed frame with images. Okay, Earth-centered Earth-fixed ECEF frame is a 3D coordinate system used to describe position on or near Earth. Okay, Earth center, the origin is at Earth center. Okay, okay, so let's tackle this together. We draw the Earth, a beautiful Earth. The origin is at the Earth center. Earth fixed rotates along with the Earth. If the Earth is fixed, so the origin is rotating along with the Earth. So okay, that does not make a lot of sense because this is still a point. A point cannot rotate because it's dimensionless. How are axes defined? That's the important thing. How are the axes defined? X-axis points from Earth center to the intersection of equator. Okay. Points x-axis. How are we defining x-axis? X-axis. So point from Earth center to the intersection of equator. To the intersection of equator. So see, if this is the equator, and I say, okay, this is the x-axis. Imagine this as a 3D ball. Okay, y-axis points east along equator. Okay, y-axis has to point east. Okay, so well, this is north, this is south, this is west, this is east. So then this has to be, sorry, y-axis. Y-axis. and so you see we have a vector coming out of here because it has to be 90 degree with this. So I mean it could be anywhere. The x-axis could be a vector coming out from here, or it could be a vector going down like this. Yeah, but it cannot be like this. Okay. It could be anything within this plane, OS plane. Okay. Z-axis points towards the North Pole. Okay, Z-axis is pointing towards the North Pole. Does it make sense now? Well, yeah, it does. So this means, okay, x-axis is coming out. X-axis cannot be this in moment because all three axes needs to be perpendicular to each other. Okay, so the x-axis comes out from here. The y-axis goes to the east. The z-axis goes to the north. Okay, makes sounds clear. Good, sounds clear to me as well. Let's open an image and let us Greenwich meridian. I don't think this is a good image to explain you. Yeah. Yeah, I think so. This is a better image. Let me put it here. See, for example, we are standing here, so I've got a couple of angles over here. See, if I stand on this plane, I can face east in this plane, I can face north in this plane. I'm so sorry, this is my frog. And I can face up in this face, and obviously all three of them are going to be in perpendicular to each other. But like for example, this is the point. So now our yref is pointing towards the east direction. So an xref has to be perpendicular to this. Okay, and z has to point towards north pole. Okay, so in fact I only need just two coordinates to define any position on the planet, and that is lambda and phi. Okay, so how much you go and how much above. So it's kind of like this. You have earth, and let's see. Okay, and okay, this. So I think so you got the idea, huh? At least I've got, and I am pretty confident in explaining with this image. Okay, that we need two coordinates in what's that called, earth centered, earth fixed reference system. Key characteristics: it rotates with the earth. Unlike inertial frame, ECEF rotates with the earth. It rotates with the earth. Yeah, so yeah, the entire even though the earth has rotated, the coordinate system has also rotated with it. So our net result, our net output, our coordinates still remain the same even though the earth has rotated, because the coordinate system itself has rotated with the earth. Okay, unlike inertial frames, ECEF rotates with the planet. That's how it is a non-inertial frame. Because if it was not rotating with the planet, the Earth is moving, and it has got a centrifugal force around it. So Earth is moving. It has got an acceleration, and that is, if you want to know, it's omega r, omega cross r. Uh, so but because the coordinate system itself is rotating, that's how it is a non-inertial frame. A point fixed on Earth, like our house in, let's say for example, Hyderabad, has constant ECEF coordinates. Okay, so our ECEF coordinates are always constant. Okay, but its coordinates change in an inertial frame because Earth spins. Okay, and that is what an inertial frame is. So the position could be written as XYZ, units are meters usually, and origin is Earth's center. Relation to geodetic coordinates, so got some relation with the geodetic coordinate, and ECEF is often converted from latitude longitudinal height using models like WGS 84. And why ECEF is useful? GPS systems, mapping and GIS. So uses GPS systems. Okay, navigation on Earth. Navigation on Earth. Okay, mapping and ground station tracking, because points on Earth stay fixed, easy to relate to maps. Okay, now we go to ECI frame, Earth centered initial frame. ECI, very important. Earth centered, and I'm gonna take my time to write it down properly. Okay, Earth, let's better type it. Earth centered inertial. Earth centered, it does not rotate with the Earth. Okay, let's see. It does not rotate with the Earth. Okay, and used for satellite motion and orbital mechanics. Used for satellite motion and orbital mechanics. Quick summary. ECEF is equal to Earth centered plus rotates with the Earth. ECEF ECEF Earth centered plus rotates with Earth. Very important. Okay, rotates with Earth. I'm repeating it again and again because you see the handwriting is horrible. I don't know. Probably I'll buy a new new tablet for this. Fixed locations on Earth essential for GPS and geolocation. Obviously, if you are going to a hospital, the location of the hospital is fixed. Yeah, it does changes to from where you are looking from, but in itself it's fixed. Okay. Okay, we can go into conversion of geodetic coordinates to Cartesian coordinates and to blah blah all of these things, but first of all let's go to ENU coordinate. Okay, ENU coordinate sounds like a United Nations charity program. So the ENU frame is a local coordinate system. Let's ENU frame. So the ENU frame is a local coordinate system. ENU frame It is a local coordinate system. A local coordinate system tied to a specific point on Earth, used widely in navigation, GPS, robotics, aerospace, or for blah blah blah. We are not interested in where it is used. We are more interested in, what is the structure of this coordinate system. So let me find some interesting images. Let's see if this one explains something. It's the same thing. Okay, these are ENU. First of all, what's the full form of ENU? Okay, key idea, local tangent plane. ENU. Okay, so ENU frames, they are different for different locations on the planet. Okay, and it is thanks for making it a circle, by the way, thank you very much. uh, uh, this ENU frame sits on a flat plane that just touches the earth at your location. So for example, we are here. So what is a flat plane passing like this? It's local, because if I'm standing here, then the flat plane passing is like this. So it's changing depending on where we are. For example, ENU axes at Bangalore are different from ENU axes of Bangalore, Hyderabad are different than of New York, or Tokyo or Shanghai. Uh, ENU is usually derived from ECEF, Earth Centered, Earth Fixed. But I want to show you some, amazing images, so that again, ground reference system, northeast up. I think so. This image does show some of these images does show. Let's go through them one by one. Let me copy it. Control V. Okay, so what's visible over here? Here is a cross section of the earth, and lots of wires. Let's put a yellow pen. Okay, so this is the point that we need to find, and so okay, it's saying go 50-degree east, go 50-degree east, then go 40-degree north, and then go some distance. What I can say is go some distance, like for example, I want to know the position of suppose it's this point. So I need to know, so first I will calculate the length of the vector. Okay, so for let's say the length of this vector is alpha, let's say. So from this direction go this much east, then go north, and where do I end up? I end up here. So from its initial position, from this point, draw the length of the vector. So here I have got my point in ENU coordinates. East, north, up. ENU, east, north, up. Okay, and let's see some more interesting images. Let's analyze them together. Even I've got no idea, we're doing it together. Let's pan the screen. Hope we are still recording. Let's take a screenshot. And it's a horrible screenshot. No, we don't need that. Control Shift S. Okay, and let's put it over here. Okay, now let's understand what this thing is giving to us. Well, I do get the point. What is azimuth, elevation and range? How high you need to look, how left or right you need to look, and how far you need to look. Azimuth is how left or right you need to look. Elevation is how up or down you need to look, and range is the actual distance. So if I make a diagram, so for example, this is the Earth. Please make it a circle. Thank you very much. I'm standing here. Okay, is there a way that I can show it to you on a 3D? We had a 3D. Yeah, we have it here. So let's say let's change some colors. Blah blah. Let's take a try. For example, I am standing here, and I need to watch something here. Okay, so how much degree did I traverse in order to reach it? This is azimuth. Okay, how up I have to look? Sorry for the, so this is theta, and this is the actual range, the distance. Now for example, if I'm looking something over here, which is, well, technically not possible, because at certain azimuths and elevations our view will get blocked. For example, if I want to look something over here, my elevation is negative. But for example, if I'm standing over here on the equator and I want to watch something over here, so how much do I need to turn? I do not need to turn anything, so azimuth is 0, and I have a big elevation of it's around 80 degrees. Okay, and for example, if something is here, so considering the Earth is perfectly sphere, this line would be a little bit tangent to this. This would be an angle theta, and this is the range. Okay. All right, let's go. So azimuth, elevation and range I've explained. Z down, K north, Y east, Z down, X north. Well, we get the idea. So as we can see in this beautiful image, let's put it over here, let's put it over here, and let's zoom it. So for example, we need to find out this point. So what angle do I need to traverse to come to this point? let's say this. No, let's take a different color, white. It's on a white background. Bloody hell. So I need to travel this angle. Let's say this angle is alpha, and from this reference position I need to look up here. Can I go a little bit up, please? Thank you very much. So this angle is theta, and this range is r. So I get three things. Now, as we have already said in the beginning of the lessons, coordinate systems are used to find points or locate positions on or near Earth. Yeah, obviously I can go and find something in infinite universe as well. The radius of the Earth is 6,371 or something kilometers. If I want to locate a point inside the Earth, okay, the r goes small. If it's outside the Earth, the r goes big with the same with the same azimuth and elevation, just the r is bigger, but that's a whole different story. So I think so that clears up a lot of things, and we can move ahead. Let's before we move ahead, let's say uh, let's study a little bit about transformation, about ENU and all of these things by rotation matrices, relation to ECEF. We take a point in concept, choose a reference point, lat long, rotate the axis, get ENU. So now we are going to learn should I, yeah, I think so. I should, make it a little bit thinner. And okay, transform ECEF to east north up. East north up. It's so earth centered, earth fixed. So ECEF coordinates are XYZ. Because they are earth centered, earth fixed, and ENU is, where is the pointer? And ENU is phi comma lambda. Latitude and longitude of reference. This is not ENU. This is not ENU. Sorry. Now we need to obtain ENU. So ENU. We need to obtain this. Okay. So it is given by the rotation matrix minus sine lambda minus sine phi and we have for example latitude and longitude, which are phi and lambda, obviously lat long, lat long, sine phi cos lambda, then we have cos phi cos lambda, then we have cos lambda minus sine phi sine lambda cos phi sine lambda then surprisingly a 0, and cos phi and sin phi. Okay, and into x minus x naught y minus y naught and z minus z naught. Okay, so this is the rotation matrix, and honestly I'm not sure how to derive this, but let's take benefit of the doubt and continue. And there are methods to convert geodetic to Cartesian, Cartesian to rotation matrix. We have and ENU is local coordinate system at point on Earth. Axis is north up, derived from ECEF by rotation. Radical equation of water. Okay. ChatGPT is just curious to give me an example. Let's walk through a clear numerical example converting the ECEF coordinates to ENU coordinates of Bangalore. Take a point near, for example, say Bangalore. So approximate its latitude, which is phi equal to 13 degree. Okay, longitude is equal to 77.6 degrees, and height is 900 meter. Let's say 900 meter. This will be our ENU origin. Step 2, reference point in ECEF using WGS80 for the reference. The reference ECF coordinates approximate another nearby point. Now take a nearby point, for example, at 1 equals slightly offset. Step 4, compute the vector difference. So the relative difference, plug the values. E N U Okay, and let's say we have a reference point in ECEF, which is 13306040. All of these are in kilometers, by the way, and 1420. Okay, and with this setting this as a reference, we need to find out another point. So for example, let's say, so this is x1, y1, z1, and 1331, let's say a nearby point 6039, and 1429. I'm going a bit crazy, but these are x2, y2, z2. Okay, so we'll find our delta x's. Okay, delta x, delta y, delta z. Okay, so delta x, delta x would be 1, delta y would be, I don't know, sorry, it would be -1, delta so would be 1, and this would be -9. Okay, equal to. Okay, and we put it into ENU rotation matrix, and we already have these things, so guys, just put it inside. I'm not gonna solve it here. What I am more concerned about is how do we get this rotation matrix, like well, I can do all those conversations. How do we get the rotation matrix? How do we get the rotation matrix? I mean, why is it the way it is? Yeah, let's ask a very simple basic question. Derive the rotation matrix. This is exactly where things get conceptually. The ENE rotation matrix isn't magic. It comes straight from geometry on Earth and how we define directions. Okay, so it's not coming out from anywhere. That's why we are trying to derive how it's coming out. We want to express a vector in Earth center, Earth fixed frame using a local basis, Earth east, north, up. So the rotation matrix is simply what are the ENE unit vectors written in ECEF coordinates. Start with position on Earth. At a point we have a latitude and a longitude. You are standing on the surface of the earth, for example. If you are standing on the surface of the earth, then we have a latitude and longitude. Okay, until here it's clear. Build the local directions. Okay, if I'm standing, I have east, I have north, I have up. I build a local direction. Let's say here are some interesting images. Okay, prime meridian, I see prime meridian, I see equator, I see let's discuss this image. So let's see what this got to offer. Oh damn, you know, it's screen recording and all. The system gets so slow. Am I on turbo mode, by the way? Silent performance turbo. Okay, let's discuss this. X is true north, Y is east, and Z is normal down. By the way, down, by down does it mean is it pointing to the center? I don't know. Okay. Here I have another interesting image. Let's discuss about that as well. Okay. So parallel, and we've got some points. Here we have. Okay, so we traverse some angle theta, some angle lambda here, then we go a little bit up, and then we go here normal to. We have to point out normal to the surface. Okay, makes sense, at least to me. That's the same diagram. Yeah, not very descriptive. North star. Yeah, actually it has got things to do with the North Star as well. Let me show you the image that generative AI is showing me. Actually, we are not even pointing towards the north. We are pointing towards the North Star, Pole Star, Dhruv Tara, as we call it in Hindi. So, if I'm standing here, I have east pointing this side, north pointing this side, and North Star pointing this side. And if I move my east vector would be changing, my north vector would be changing, but okay. Let's go a little bit crazy here. So for example, I am moving, consider this as to be 3D. I am moving here like this across the surface. So my east vector is changing. I'm changing the angle. My north vector is also changing, but my up vector is not changing. For example, if I'm walking like this on the surface, like this, now you see my north vector has changed. My north vector has changed. It was something before, now it's something after that. By the way, because this is a 2D image, actually when we moved in this direction, even then our north vector changed. Yeah, because it's 3D, and I think so we should do something to, you know, make some technology that could make screens display things in 3D, actual 3D, not after slicing down things and pretending them to be 3D. Okay, that long, and all right, so that's all. I want to let you know as well that we have, and then there are methods of measuring times. So time in measurements of time. Uh, so measurements of time. Let me write it. Is there any way I can short edit the size? Edit duplicate. No, it's so big. Yeah. Okay. Time measurements. Time and time measurements. First is solar time. Second is sidereal time, and third is atomic time, and this is not a method. Time epoch, since when time measurement and time source stability. Okay, so what is solar time? Solar time, I think so it's better to write I mean type solar time, the amount of time the earth takes to make a full rotation on its axis. We are going to go into detail, so don't worry. Okay, now what is solar time? Then we have sidereal time. Okay, so ChatGPT is taking me into much more details like apparent solar time and mean solar time based on actual observed position of sun. When a sundial shows, what a sundial shows is apparent solar time. Okay, and Earth's orbit is elliptical. For example, solar moon is not exactly 12 p.m. IST, 20 p.m. until 15, so depending on the day, because IST is fixed for the whole region, but the sun isn't exactly. Okay. Let's say sidereal time. What is sidereal time? So it is a way of measuring time based on the rotation of Earth relative to distant stars instead of the sun. Sidereal time tells you what stars are overhead right now. Poor idea. Earth rotates once relative to the sun. Solar day is so solar day is 24 hours and sidereal day is 23 hours 56 minutes and 4 seconds. Now here I would like to explain you why this difference is. Solar time is the amount of time it takes. Uh, Actually, I've written the wrong definition. My bad. So, solar unit time. Okay, let's call it solar unit time. Solar unit time. Unit time. Amount of time it takes for the sun to return to its original position. Okay, makes sense. So I say the sun up somewhere after one solar day at the exact same point. When the sun is at the exact same point, I have one solar day. Sidereal time, it's relative to distant star, not with respect to the sun. So when the earth has rotated on its own axis completely, the point which was facing this side now is facing this side again, and is facing the same distant star. Now why do we take distant star? Because it's so distant that any lines coming from it is apparently parallel. They're literally parallel. But why there is a difference? Solar time is 24 hours and sidereal time is 23 hours and 56 minutes. We say no, we have a day of 24 hours, 24 hours, and here we have 23 hours, 56 minutes, and 4 seconds. So let's say this is the sun and this is the orbit of the earth around the sun. Wow, what a beautiful sun in orbit. Now here is the earth. Okay, it's moving around in elliptical path. Now if I look at this point, in around 24 hours, I'm here and I'm rotating, and as I'm rotating I'm also moving forward. Okay, so the earth has rotated itself completely in 23 hours 56 minutes and 4 seconds, but because it has also moved forward a little bit during those 23 hours 56 minutes and 4 seconds, the sun is left behind a little bit. Okay, so in order for the sun to return to the same position again, that's the difference of 4 minutes, 3 minutes 56 seconds to be exact. Okay, so try to understand this. Suppose I'm here and I'm just standing here and I'm rotating. Okay, this is just rotating, it's not moving along this path. So I will take X amount of time, this point will take X amount of time to come to this point, okay, to face the sun again. Okay, this the way it was facing before. Now what happens is, as I am rotating, I'm also moved a little bit forward. So now for this point to face the sun, uh, to have the sun at the exact same location, we need extra 3 minutes and 56 seconds. So this is the sidereal day. Okay, that's how it's kind of intuition, because as we are rotating, we are also revolving around the sun. So long story short, a sidereal day is approximately 4 minutes shorter than a solar day. Let's say visual intuition, CCC, is a very classic example. Let me share with you the screenshot, and here we have paste. It does not want to paste. Let me paste it this way. Okay. See, sun and distant star are overhead. Sidereal day, distant star is overhead again, but not sun. Distant star is still overhead because it's very distant. Like, sun is not a distant star, and here, as the earth has rotated, now I'm pointing this way, but solar day, sun is overhead again, but about 4 more minutes have passed since sidereal day. Okay, so try to ponder over it a little bit. At least I've understood what's the crux of this sidereal and solar day, sidereal time and solar time. North celestial pole, star classical equinox, and we have south celestial pole, north celestial pole. Great amount of, see, the best of the best diagram I'm going to show you guys now. The best of the best. You just get out. Literally, see it. Clipboard, obviously allow. Okay, so let's zoom it in. See, after one day, the Earth has revolved around the Sun by approximately 1 degree. Yeah, exactly. See, the Earth requires 365 days to complete 360 degrees of rotation revolution around the Sun. So, in one day, it's moving a little bit more than 1 degree. Okay, so in one day the number of degrees moved is 365 by 360. We have to make up for it. Okay, the earth completes one full rotation per sidereal day. Okay, one full rotation of earth is in sidereal day, it's not in solar day. After the earth has revolved around the sun, it has also revolved around the sun. It needs to rotate a further approx 1 degree. Okay, it needs to rotate approx 1 degree to bring it back to sun in line. Okay, now I think so this is the most clearest image and description. So we need to turn an extra 1 degree. Okay, that's why one solar day is 24 hours, one sidereal day is 23 hours 56 minutes 4 seconds. So the earth itself rotates on its axis in 23 hours 56 minutes and 4 seconds. Okay, oh, lots of energy. So what's the radial time actually measures? The right ascension currently crossing your local meridian. Okay, this has to celestial coordinate system. We'll go into that. Local sidereal time, Greenwich sidereal time, white matter sidereal astronomy, pointing telescope, satellite tracking, spacecraft navigation, converting between Earth and space, frame connection to the domain in orbital mechanics. ECI, Earth-centered initial frame, is aligned with stars. ECEF rotates with Earth. Actually, with ECEF, I'm like pretty clear, but ECI, somewhat still confuses me. LST, what was LST? Local sidereal time. At a given moment in Hyderabad, for example, if local standard time is 10 hours, a star with RA. What is RA? Why do these guys use so many abbreviations? Sidereal time measures the Earth rotation relative to distant star, telling you which stars are overhead at any moment. Okay. Okay, we are not going into a lot of formulas here, but I hope that make some shed some light. Now we should move forward with atomic time and time epoch. Okay, atomic time is like pretty simple. Atomic time. What is atomic time? Atomic time is a way of measuring time using natural vibration of atoms. Instead of relying on the rotation of Earth around the sun and blah blah all of these things. Atomic time is the most precise way and stable way to measure time. Okay, atomic vibrate at extremely consistent frequencies, and actually, 1 second is defined as the time period of a cesium 133 atom. If I'm not wrong, cesium 133 atom. My lectures are gonna be boring. I'm not doing it for views, but so yeah, that's how a second is defined. The official definition of a second is 1 second is equal to, I don't know what is this, 1 2 3 4 5 6 7 8 9 10, 100, 1000, 10,000, lakh, 10 lakh, crore, 10 crore, 9 Arab, 19 crores, 26 lakhs, 31,770 oscillations. So the duration of time in which a cesium 133 atom does these many oscillations is 1 second. This is the foundation of modern timekeeping, and timekeeping is extremely important when we talk about navigation, because you'll get to know. You'll get to know. Cesium atoms change energy states. Is there a way to pause? Yeah. Has it started? Does it not look like it has started? 1 hour, 11 minutes. Okay, it's just showing me the minutes, not the seconds. It will probably show me the seconds as well. So we were talking about the atomic time. Yeah. Let me see if the yeah, recording has started. Yeah. So atomic time is built from hundreds of atomic clocks worldwide and extremely stable. They're extremely stable. Errors are of nanoseconds. That's how we get pretty precise navigation on Earth, because all the GPS, GLONASS, BeiDou, Galileo, GNSS, Navic satellites up, all the GNSS navigation systems up there are using atomic clocks. Okay. Solar time is measured by sun, sidereal time by stars, and atomic time by atoms. Extremely precise. Good. I mean, historically, we talk about previously how do people used to measure time by looking at the sun. It has not come up yet. It's night. It has started to come up. It's dawn. It's overhead. It's noon. It's starting to go down. It's dusk. It has gone down. It's dusk. Later dusk. Totally down. Night. Okay. Coordinated universal time based on atomic time, and this keeps clock aligned with Earth's rotation. Uh, Again, atomic time, it's very important in GPS systems, satellite navigation, space missions, telecommunication, internet synchronization. Even a tiny error, large position errors in GPS would occur, and we will get to that. Why time is actually the measure of distance, of position in navigation. Okay. Okay. And let me just share a couple of words on time epoch. As per my information, I do not need to search it, but what it means is where do you start from in time. Time epoch is simply a reference starting point in time from which measurements are made. Epoch time, I start from 1st January 12:30 noon and 46 seconds, say for example. So that's my time epoch. Everything is happening after that. My analysis is going after that. Okay. So instead of epoch time is time equal to 0 for a given system, instead of saying this happened on some date, this we say this event happened x units of times after the chosen reference frame, after the chosen epoch. Okay, this is epoch time. Okay, usually epoch is used a lot, and this is the core of timers actually. Okay, we want to measure 20 seconds, 20 seconds from now. Okay, so now is the epoch, and 20 seconds we measure. So historically speaking, GPS has an epoch. When did GPS started? It started on 6th of January 1980. And why epoch is critical in aerospace and orbital mechanics? Orbital elements are defined at specific epoch. Satellite position at epoch t naught. Okay, I say that, okay, this is the satellite position right now. I want to know the position at time right now plus t naught. Okay, propagate forward in time. Without an epoch, the data is meaningless because everything changes with time. Okay. So t naught is epoch, t is current time, and delta t would be t minus t naught. Okay. Some system different epoch, position at t, 0 position at time t, 10,000 different values, time equals a fixed moments used as starting points for measuring times in the system. Epoch is the 0 point of time. Let me write it down, type it down, to be honest. Can I make it small? Yeah. Epoch, 0 point of time. Epoch is the 0 point of time. Okay, so let's move on to some next slides. My slides are time source stability and oscillator stability. I mean, oh, time source stability. Let me touch this topic briefly. Time source stability. ChatGPT helps a lot, but time source stability describes how consistently a clock keeps over a time period. Oh, a stable clock takes at a constant rate without drifting. Hmm. We have realized that over time our wristwatches, I don't know, because of pure battery, they drift a little bit back, and we need to retune them. That's bad. I mean, for us, it's a matter of minutes, but 1 minute is a big difference in GPS navigation. If you is humongous. It's totally unacceptable. Okay. Visual frequency is equal to ticks per second. Long term, how is it measured? Allen deviation. So we have to do in navigation. Time error is equal to position error. Position error is equal to velocity error. Okay. And same goes for acceleration as well. Now, and obviously these atomic clocks are based on some oscillators, and those oscillators need to be stable, and that's another deep research subject which we are not going to touch here. There is some Chinese mind map which let it go. Okay, the International System of Units, the SI is System International, is a system of units in which the unperturbated ground state hyperfine transition frequency of the cesium-133 atom CS is 91926317770 hertz. Time baseline. Okay, this is the number of vibrations this cesium atom does in 1 second. Speed of light in vacuum, we know it's 299792458 meter per second. Planck's constant is 6.6260715 into 10 to the power minus 34 joule second. Great, thank you for telling such a beautiful constant. Elementary charge is 1.602176634 into 10 to the power minus 9 coulomb. Avogadro Boltzmann constant is 1.380 649 into 10 to the power minus 3 joule per k. I don't know what's k. What is unit of Boltzmann constant? Unit of BOLT is Boltzmann constant. Let's write it down. Elementary charge is coulomb, we know. J by K, a joule per Kelvin. Okay. Boltzmann constant, joule per Kelvin. Your unit of Boltzmann constant is joules per Kelvin. Unit of BOLT is a Boltzmann constant is joules per Kelvin. Okay, Avogadro constant, it's used in like mole concept of something. Of constant, and A is 1.0221407 into 10 raised to the power 23 per mole. The luminous efficacy of monochromatic radiation of frequency 540 into 1024 Hertz KCD is 643 lm per watts. Luminous efficacy. Let's say, what is the unit of, what is luminous efficacy? Luminous efficacy measures how efficiently a light source converts power into visible light. A light source converts powers into visible light. It tells you how much useful light you will get per watt of power. Luminous flux per power. Okay, lumens per watt. It's measured in lumens per watt. So incandescent bulb 10 to 15 lumens per watt, and fluorescence bulb is 15 to 100, and LED is 100 to 200 plus. Important detail, luminous efficacy depends on human eye sensitivity as well. Human eyes are more sensitive to green light, so not all watts of light are equally visible. This is described by luminosity function, two related terms. Luminous efficacy of radiation, why it matters, energy efficient lighting, LED tech, satellite and spacecraft power budget, solar power system, optical system design. Luminous efficacy is how much visible light you get per watt of power. Luminous efficacy is how much visible light lumens you get per watt of power. You get per watt of power. Lm per W. Okay, so that's done. And can I somehow drag this thing here? Okay, it does not want to get dragged. Okay, we can go into a lot of things like what is luminous flux, intensity, luminance, and you know that would severely deviate us from the core of this lecture. Okay, let's go on to the next slide. Okay, we come on to time measurement. If you want to measure time, we observe a periodic process, count the cycles, period, rotation of the earth, day, earth revolution around the sun, that is a year. Time is equal to range. 1 second is equal to 3 into 10 raised to the power 8 meter. Yes, 1 second is actually a distance that is traveled by light in 1 second, which is 3 into 10 raised to the power 8. It's 2.99 something, but we rounded it off to 8. We rounded off to 3. Okay, so 1 millisecond is equal to 300 kilometers, and 1 microsecond is 300 meters, and in 1 nanosecond the light travels 0.3 meter in 1 nanosecond. Time of day. Wow. in 1 second, it's 3 into 10 raised to the power 8, 80. What's that? 300,000 kilometers in 1 second, and in 1 millisecond, it travels 300 kilometers. 1 microsecond, 300 meters. That's insane speed, man. Come on. Okay. So we measure time by using crystal oscillators. Okay, these are the most efficient, accurate, reliable modes of time measurements. Crystal oscillators, CRYS, crystal oscillators, VCO, comma TCXO, comma OCXO. So crystal oscillators, all these are ways to generate a stable clock signal using a quartz crystal. The crystal vibrates at a precise frequency like a tiny tuning fork. The difference between them is how well the controller adjusts that frequency. Quartz exhibits the piezoelectric effect. Apply voltage, it vibrates. That vibration gives a very stable frequency. VCO is a voltage control oscillator. Text oscillators, crystal oscillators. Let me write properly. Crystal oscillator. So VCO, voltage control oscillators. Frequency is controlled by its frequency is controlled by an input voltage. Frequency is apply to voltage. So it gives us wide tuning range but lower stability than others used in PPL systems. Okay, gives wide tuning range, but lower stability due to voltage could be varying, and used in PPL system. I don't know what is a PPL system. I hope it's not a private pilot license system. TCXO, temperature compensated crystal oscillator. TCXO, temperature compensated CRY crystal oscillator. Compensates for temperature variation. Quartz frequency oh yeah, exactly, frequency also changes with temperature. You can try it yourself. I mean, take a fork at your home, heat it on the stove, and strike it. Take another fork, put it into the freezer, let it cool down, then strike it. You'll feel the difference. But its frequency changes, quartz frequency changes with temperature, as quartz frequency changes with temperature. TCXO corrects it. Electronically much better than basic crystal. Small and low power, and common in GPS receivers and mobile devices. Okay, well, anything whenever you're stuck in an interview, just say it's used in GPS receivers. If you want to impress them further, say it's used in GLONASS, NAVIC, QZSS, BeiDou, Galileo. They're like, oh, this guy knows a lot. When it's actually, it's impressive. We are putting our effort. Okay, then we have OXCO. OX, OXCO, OXCO, OXCO. Keep the crystal. Keep the crystal at a constant high temperature and set a time. Okay, O1 control crystal. O1 controlled CRY crystal oscillator. Okay, so we see the drawback of the TCXO being overcome by the OCXO. With varying temperature, the frequencies was changing, but with the OCXO, we are putting it in a tiny oven and where the temperature is constant, so that the frequency remains constant. So instead of correcting and maintaining temperature, we eliminate temperature variance. Extremely high stability, slower startup, but I think so this is a trade-off I could easily accept, because missions are usually under planning for like years, and I could wait for those years to get my clock synchronized properly, so that when it's on the mission it remains synchronized. Okay, precision timing labs and blah blah, one line research. Okay, so output central frequency, we have atomic clocks, 1 ppb. What is 1 ppb? Yes, 1 ppb. ppb means 1 part per billion. Okay. Okay, now we have optical clocks versus nuclear clocks. Great, it's going great. Where is the pointer and how long has been this? 1 hour 33 minutes. No worries. Optical clock versus nuclear clock. Okay, I can just say a couple of words. What are optical clocks and nuclear clocks? Optical clocks versus nuclear clocks. I mean, here are just diagrams. If you want, I could show you the diagrams. Let's see if we could make something out of them. Actually, this is a classified file. I'm not supposed to share it, but still. Optical clocks use electronic transition in atoms like strontium or ytterbium, operate at optical frequency, very high frequency. Higher frequency is equal to more ticks per second, better precision, stability level, error 1 second in billions of years. Optical clocks gives an error of 1 second in billions of years. Great. You they use electronic transi transition in atoms like strontium or ytterbium. Why they are, I mean, if it is giving 1 second error in billions of years, I literally don't care. My grandchildren's 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 would have passed by then. Why they are powerful, already outperform traditional cesium clocks. Okay, so optical clocks are superior than cesium clocks. Already outperform, used in defining the second relative experiments, geodesic universe gravity variations. Okay. Nuclear clocks use nuclear energy transition inside the nucleus, not electrons. Most promising candidate thorium 229. Okay. Nuclear clocks. Thorium 229, much less sensitive to, it's much less sensitive to external disturbances and more shielded than electrons. Its potential could reach, in theory they are more stable than optical clocks. Okay, so I mean, both of these things are, at least nuclear clocks are in experimental stage. They are not a reality as of now, but if when they become, it's going to be still in experimental stage. Transition type optical clock, key differences. Optical clocks today, best practical clocks today. Optical clocks, can I just simply not drag it? Oh damn. Most practical clocks today possible with current okay. So we have covered a bit about optical clocks and nuclear clocks. Thorium 229 much less sensitive to external disturbances, still in ideation stage, and optical clocks are a bit of reality today. Clock accuracy and stability. Accuracy, frequency departure from a specified value. Stability, frequency source output within a specified range over a period of time. Okay. It's 1 hour 39 minutes already. Oh, I'm damn good. I'm damn good. Accuracy is frequency departure from a specific value. Stability frequency source output within a specified range over a period of time. F is equal to f naught plus delta f plus t naught tf plus random Allen variance phase noise p is the accurate but not stable. Not stable, not accurate. Stable but not accurate. Stable and accurate. I can give you a diagram directly here and explain what it says. You can see it's stable but not accurate. I want f naught. I want f naught. Okay. I wanted this value. I wanted this value and it started giving me something else. So it's stable but not accurate, and you get the idea. It's not, it's not stable, not accurate. It's accurate but not stable. It's both stable and accurate. Plus plus. It's accurate, not stable. It's minus minus. It's stable but not accurate. Okay, so let me write down the formula. F equal to f naught plus delta f plus t plus minus t naught df by dt plus f star t. Okay, now clock bias, how does it relate to accuracy? Okay, clock bias estimate meter, RB oscillator, CS oscillator, OXO. What was OXO? We just studied it. Oh, something optical flow. Temperature control oven control crystal oscillator. Oh, so you see clock bias, CS standard, TCXO, OXO in time, hours. Okay, kind of strange. RB oscillator, CS, TCXO, OCXO, oven controlled crystal oscillator. Now clock drift. The clock drifts, that's it. That is what I can say about it. Satellite clock error correction. So delta root of semi-major axis, eccentricity, mean anomaly, reference epoch, argument of perigee, inclination at reference epoch, longitude of the weak, mean motion difference, rate of inclination angle, connection, like this, broadcast, orbit, ultra predicted function, GLONASS, explanation, TFS. Okay, then we have satellite clock errors. The satellite clock reach up to more than 150 kilometers. Okay, so small errors in time measurements could reach to, if I am sitting in Kota, it could show me that I'm sitting in Jaipur, 150 kilometers. Random noise characterization. Allen variance, Hadamard variation, phase noise PSD. Uh, uh, really not in the mood to write on this weird tablet. Allen variant, random noise characterization. Random noise characterization. So sorry, I've got a bad throat. Okay, let's go to ChatGPT, Baba. Random noise characterization. Allen variance. Hadamard variance. Phase noise PSD. And I would really say explain like a child. So at least we let me write a formula. Allen variance for Allen variance, until then it's become its child. Allen variance sigma y square tau is equal to 1 by m yi plus 1 minus yi whole square, and Allen deviation sigma y tau equal to 1 by n, sorry guys, this cuff equal to 1 to n 1 by 2 yi plus 1 minus yi whole square. Alright, let's make it feel simple and intuitive. Imagine you are listening to a perfect steady tick 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 from a clock. Now real clocks, especially oscillator like TCXO and OCXO, are not perfect. They the ticks wiggle a little. The tiny wobble is what we call a noise. Yeah, any disturbance, no matter how perfect you make it, you're still gonna have disturbance. Okay. What is random noise in time? Perfect clock, evenly spaced ticks. Real clock, slightly early, late ticks. That randomness, noise and time frequency. Now, how do I explain the three tools? Allen variance, Hadamard variance, and phase noise. Allen variance. Uh, let's compare neighboring ticks. Take two nearby chunks of time. Check, did the clock speed change? Intuition, if the clock is steady, differences are small. If it's noisy, differences are big. Simple analogy. Imagine you walk 10 steps every minute. If you suddenly walk 9, then 11, then 8, then Allen variance measures how much your walking speed changes between steps. What it's good for? Most common way to measure time stability is for oscillator GPS clocks. Hadamard. Hadamard variance. Let's ignore slow drifting and focus on real randomness. Sometimes clock drifts slowly, like getting tired. 10, 10.1, 10.2, 10.2 slow drift. Allen variance get confused by this. Hundred variance says ignore slow trends, only look at the true randomness. A car slowing going uphill but also shaking randomly. When long-term Hyderabad is used when long-term drift is present, very stable clocks, phase noise, power spectral density, PSD. Let's see what kind of noise is inside the signal. Think of noise: bass, low frequency, treble, high frequency, phase. At which frequency? Okay, just how bad the clock noise and time domain, the time domain to resistance wave noise frequency domain 1. Allen variance compares neighboring timing errors. Hadamard removes slow drift. Where's noise slows how noise is distributed across frequencies. Phase noise density, PSD, is power spectral density. Guys, let's sorry. uh, let's give this image to ChatGPT and ask, dude, what do you have to say about this? This is actually a really good slide, basically showing the full story of oscillation as in one picture. Let me break it down the way that is a big picture you're looking at. You're seeing phase, the source's frequency offset from a carrier. X-axis, how far are you from the carrier noise level? The red line is the important part. It shows how noise waves are different regions. The key idea, the red curve is not random, it's made of different noise types, each dominating an area. It's very close to carrier h minus 2 steep slope down random walk frequency news. One is wandering like drifting clock. Okay, guys, if you understand it, I understand it because I'm off. Hmm. Oh, sorry for my I just didn't realize I was being recorded. It's pretty late and I'm chewing a chewing gum. Alien variance. The marked variance wasn't in order to address the deficiency of Allen variance in distinguishing between WH, H, and LPH. Okay, short-term, long-term stability. Quartz, rubidium, cesium, GPSO. Life expectancy depends on electronics, usually more than 10 years. Rubidium. Cesium is 5 to 10 years, depends on electronic, more than 10 years. Frequency accuracy after 30-minute warm-up. No guaranteed accuracy, must be set on frequency. 5 into 10 is to the minus 10, 1 into 10 is to the minus 12. Stability at 1 second. Parts and 10 is to the power 10. Stability in 1 day, 1 into 10 is to the power minus 10. 200 to $1,000 $10,000 to 8,000, 35,000 to $75,000. Okay, makes sense. See a very interesting slide. Uh, just imagine how much expensive a cesium clock is. It's the best one could be like $75,000 bucks. So here are some B BDS3 satellite clock. What is BDS3 satellite clock? Oh, BDS means BeiDou, and they use hydrogen atomic clock and rubidium atomic clock. GPS satellite clock, first GPS. Cesium clock, first GPS rubidium clock. Cesium, rubidium, hydrogen atomic clock, and rubidium atomic clock. So clocks. Let's write clocks. Clocks. Rubidium clocks. Cesium clocks. And GPS rubidium. So data source is something BDS, GPS 3 clocks, Galileo FOC clock data processing using MAD, voice, drift, noise, performance indexes, calculating, fitting the settings periodically. Finally, we are at time scale. Two independent requirements, astronomical precision requirements. Let's move on. Time scale. Astronomical requirement match with the earth rotation precision requirement. Time scale definitions. Solar time, sidereal time, ephemeris time. Universal time, Greenwich time, local time. International atomic time, universal coordinated time, Julian day, modified Julian day, GNSS time. So let's write them one by one. Solar time, sidereal time, ephemeris time, universal time, Greenwich time, local time, which we are mostly used to, international atomic time, universal time coordinated, Julian day and modified Julian day. I would love to know about the GNSS time. GPS, BeiDou, Galileo. So let's take their definitions one by one. Definitions. So known highest point used historically is solar time. We know ephemeris sidereal time is relative to stars used in astronomy, which star was overhead. Ephemeris time introduced because Earth rotation is time based on planetary motion used for precise celestial mechanics, replaced by Earth rotation. Universal time based on Earth rotation. It is corrected. It is not Greenwich Meridian time means solar time at Greenwich Meridian. Civil time systems regional using the same standard based on longitude. Local time, daylight saving atomic time, international atomic time, and continuous time based on atomic non-leap cycle extremely stable. Coordinated universal time 7 standard time. Oh, what's Julian day? Continuous day count of days since I would really love to write what is Julian day. Continuous count of days since Jan 1 4713 BC. Modified Julian day is equal to JD minus 24 5.5. GNSS time systems have all GNSS systems is the atomic scale independent. No leap second observed from current. Similar to GPS time patterns, atomic time GLONASS is the 1% UTC includes leap seconds, different from GPS and BeiDou scale. Time is atomic time very close to key relationship. Think of it like Earth is solar time, atomic stable TI hybrid. Solar is not stable, sidereal astronomy. Earth rotation, atomic cause, reference standard, UTC civil time. UTC civil time, Galileo atomic UTC based one line master time system differs by water reference solar day. Earth rotation, Earth clock or continuous counting, JD, MJD. Okay. Meridian and equator. We know that the Earth is a circle. It's I mean, not a circle. Okay, let's use. So somewhere around England there is one line passing that is 0 degree latitude. 0 degree latitude. Alright, and then we have the equator, 0 degree longitude. Apparent solar day and mean solar day. Solar time. Okay, apparent the time between two successive transits of sun across a local meridian plane. Earth orbit is elliptical, non-uniform orbital speed. Earth rotation axis is not fixed. So apparent solar day is plus minus 4 degree, which is plus minus 16 minutes per year. Mean solar time, hypothetical circular orbit. Let's say the orbit of the Earth is hypothetically circular, same period as the real orbit. Mean even orbital speed, open goal rotation axis. Sidereal apparent time, apparent sidereal day, the time the Earth takes to rotate once on its axis related to distant stars. Spring equinox. Mean sidereal day. Mean sidereal day is less than mean solar day. Let's write it down. Mean sidereal day is less than mean solar day. One mean solar day, one mean sidereal day, one mean sidereal day is 23 hours 56 minutes 4.0954 seconds. Okay, quiz 1. Why is mean sidereal day is about 4 minutes shorter than the solar day? We have already answered that, because as the Earth is rotating, solar day is when you see the sun at the exact same spot, on which you saw it the previous day. But since the previous day sorry for the WhatsApp message. Since the previous day the Earth has also moved a bit ahead in its orbit, so it needs to steer a little bit to the left, a little bit behind, so that the sun is exactly in the same position. So it takes 4 minutes more for the solar day than a sidereal day. Universal time unit, time scales based on rotation of Earth, time standard before 1960. UT0 means solar time at the prime meridian orbital from astronomical observations subject to observable spin rate at polar motion. Greenwich meridian time, UT, local time, 360 degrees, 24 time zones, 24 hours. One time zone equal to 15 degree, prime meridian at 0 degree, and then we divide it into 15 degrees. So like Okay, so this is Earth, and we have 15 degree. Prime meridian as 0 degree. Time zone equal to 15. One time zone is equal to 15 degrees. One uh, time zone equal to 15 degree. By the way, don't worry, I'm going to attach this canvas into the YouTube description. I know it's been really long now, so 2 hours of video, 2 hours and 16 minutes. But we are about to finish, and for a reference, here you can see how time is divided. So we see here, and then we go down there, not like this, like this, like this, and then we go first. Okay, hope that answers. Just pause the video over here and see if you want to. Okay. Okay, ephemeris time is in principle refers to the time in association with an ephemeris, itinerary of the trajectory of an astronomical. What is ephemeris? First question. What is ephemeris? Information regarding the trajectory of an astronomical object. Proposed in 1948, based on Earth revolution period to overcome dislocated mean solar time. A former standard astronomical time scale was developed in 1952 by International Atomic Union and replaced by terrestrial dynamic time, TDT, or barycentric dynamic time, TDB, in 1976. Then in 1991, TDB was renamed as terrestrial time, TT. ET minus TAI. Okay, this is going too crazy now. International Atomic Time, TAI. Current time standard definition. Today, what are we considering standard time today? It's 1 second is the duration of 919263170 periods of radiation corresponding to the transition between two hyperfine levels of ground state of the cesium 133 atom. TAI is a weighted average of time kept by over 400 atomic clocks in over 30 countries, over 50 national laboratories worldwide. Reference level advantage is something. Universal coordinated time, UTC. UTC is compromise between universal time and TAI. What was TAI? International Atomic Time. I think it's a reverse abbreviation. It should be IAT. It reduces leap seconds in UTC to keep stay uniform accurate while considering the Earth rotation effects. So adjusted on last second of June 30 or December 31 of every year. So let's see. What's this? 1900, 31, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 37. I don't know what they have done, but they have done something. Okay. Julian day is continuous counter since the beginning of the Julian period and is used primarily by astronomers and in software for easily elapsed day. Julian day number 0 is equal to 12th of 12 p.m. Jan 1. Julian day Jan 1. What's 713 BC. Julian period by solar cycle into lunar cycle, 28 solar cycle into 19 lunar cycle into 15 induction. Oh, in such and such and such time some things are going to happen. The Julian period is a long time cycle created so that three repeating calendar cycles line up again at the same time. Okay, so 28 solar cycles, 19 lunar cycles and 15 induction cycles. After 28 years the calendar repeats, same dates fall on the same weekdays. Oh really? Lunar cycle, after moon phases repeat on the same sides. After 19 years moon phases repeat on the same side used in ancient calendars. Induction, repeat every 15, a Roman Hellenistic cycle, not astronomical, purely historical. Okay, so this is just a brief history. Julian, there is some induction period. Why this was useful? Julian period was created by scholars like Joseph Smith to avoid confusion between different calendar systems. The events connection to Julian period is equal to long cycle. Julian day continuous countdown within that system. GNSS time of week number modulo 1024 plus seconds of week. 1 year is equal to 52 weeks. 1 week is equal to 6,48,000 seconds. GPS time TI defined by a set of CS and RP clocks at GPS monitor stations and onboard satellites in real time and continuous, no leap seconds. First cycle starts midnight. GLONASS time TI hydrogen clock. And by the way, this is some important information that you people might like. Just go through it. Okay, Wednesday 2173 2174 weekday. So we can also define a GPS week number, I guess, and here is how you do it. Try to understand it yourself. You guys are smart enough now. If you look about September 21, this is a GPS week that's going on since the epoch of GPS on, I think so, 12th of January 1980. Okay, and okay, see, definitely we cannot remember all of these definitions, so I'm just giving you a screenshot. Oh, damn. Relationship of time reference. Amazing, amazing. This is an amazing picture. Okay, theory of relativity. Special relativity applies to all physical phenomena in the absence of gravity. General relativity explains the law of gravity to other forces of nature. It applies to cosmological and astrophysical realm, including astronomy. Application: high speed, near light speed, strong gravity. Curved space-time. You know, space-time is curved. Let me show you how. Black hole, man. Such weird things exists in the universe, like a black hole. See, if Earth is here, space and time is bent. GNSS time correction. Oh, special relativity, time runs slow on high speed platform. Yes. And T1 equal to time runs fast when gravity turns weak. That's going into like way theoretical, way across the scope of my explanations per se. Periodic relativistic effect, Earth rotation corrections, Sagnac effect, Sagnac effect. I am just pasting this last article because it's already very late, guys, and I'm done. Done. Just this is Sagnac effect. Right. So I think I should hit the bed now.